Today we're going to be talking about strategy for the butcher. Second boss in high mall, of course. What? All right, list one type of interprocess communication. We have message passing, signals, shared memory. So any of those three would have been acceptable. If you babbled on about some stuff, you maybe could get some credit. But you could have maybe said pointers with some explanation. Maybe. That would have been okay. Specifically as it involves forking Abe. Because if you have the pointer set up pre-fork, then they would both have the essentially shared memory, but it predates shared memory. All right, questions on that? Did everybody get that? Or some form of it? It was like one step easier than or one step harder than just an attendance quiz. So if you miss this one, just be embarrassed. Or watch the video when you skip class. All right. So I think our last comment we had right as class was getting out, Abe incorrectly answered.
Only theoretically incorrect.
Theoretically, yeah. In a really poorly written operating system, I suppose. So the question was, does fork duplicate only the calling threads or all threads? So it really makes the most sense for it to duplicate only the calling thread, because chances are when an individual process already has a bunch of worker bees doing some work for it, when it makes a copy of itself, chances are a duplicate of all those worker bees isn't necessary. In fact, in many ways, it might not make sense, especially if they're already working on that task. You know, kind of like you got a bunch of guys changing light bulbs, and just all of a sudden you ship over some new dudes. They're like, I'm here to help to change the same light bulb. Kind of doesn't make a whole lot of sense. So even theoretically, your answer is pretty poor.
Nice.
But it is an interesting discussion to think about how threads are duplicated and what makes the most sense. So this kind of comes down to how the threading model works in most operating systems, really whether we're dealing with pthreads or one of the other threading libraries, pthreads being the Unix one we talked about last time, just at a very high level. What was it talking about? Oh, threads, you have a parent thread that involves the process. And so that's when a process is born, it has one thread of execution by default. Then when it spawns off other threads, those threads become the children of that calling thread. So only the calling thread, the main thread of execution, is what's duplicated. Okay. See, that would have been a funny thing to do, is like hit this, like, everybody take out a piece of thing. It's like, we just did this. No. Okay, thread cancellation, terminating a thread before it finishes. So instead of letting a thread naturally come to an end, we looked at our Java example, or just the run method. Typically what I like to do in run methods, since we usually think of threads as being kind of an ongoing thing, not always, but often, I like to throw an infinite loop in the run method, which probably isn't the best programming practice, but kind of my MO for programming along those lines is throw in an infinite loop and have it constantly checking some global variable that I can set externally. So that's how I do my inner thread communication, is have each instance of a thread just keep doing what it's supposed to do until somebody notifies it that it should stop. Okay. So two general approaches: asynchronous cancellation terminates the target thread immediately. So you would have to have some sort of direct access to the thread object. Thread objects in Java do have a command to immediately kill it. So as long as you have a pointer to that thread, the thread's off running on its own, but whoever spawned that thread and told that thread to start does have a pointer to that thread. So an approach for that might be, if I'm the parent thread and I'm spawning off 50 workers, I might throw those workers into a linked list or an array if you know exactly how many threads you're going to have. And then when I want to start killing off children, when I go on a killing spree, just spin through that linked list and issue the kill command for each of those threads. But you have to maintain those pointers. What's this? Children, yeah. Issue the execute. No, it wouldn't be execute. Kill, yeah. The massacre command for each of those children. Okay, let's see. So that would be the direct way of doing it. Deferred cancellation allows the target thread to periodically check if it should be canceled. That's kind of the one I like. Rather than having all these extraneous threads sitting out there with pointers. I like each thread to just kind of be on its own for determining whether it should keep going or not, whether that's through an interprocess communication technique like shared memory or not. I kind of do my own version of shared memory, where I just have a variable at a field in the thread object that I set, and every single time through the run method or every so often through the run method, it checks that variable, and if it should kill itself, then it does the suicide thing. What's up? That's right. That's right. I outsource the killing to the target. Never work in the movies. It would never work in the movies, but computers it does. All right. Signal handling. Talk about this briefly. We've already talked about it quite a bit. Signals are used in Unix systems to notify a process that a particular event has occurred. How many of you in here have done iOS programming? Have you run into, I know you have, I think, NS Notification Center? Have you seen that before? So NS Notification Center is kind of an implementation of signals where a individual thread can decide, I am interested in hearing updates, getting push notifications, if you will, about certain events that might occur. So a thread can register itself with the notification center in iOS or the signal core in an operating system and say, any signals involving these things I'm interested in. These other things don't bother me. Make sense? So an individual thread can register itself for being interested in certain signals, and it will receive a copy whenever somebody rings the bell, sends the alarm. It's not a direct communication, it's an indirect communication. So if you're another thread and you're going to raise the alarm, all you do is shake the bell. And anybody who is interested in hearing that particular signal will become aware. They'll hear that bell and then can act appropriately for what they should do. Suicide or switch tasks to something else, whatever. Okay. So that's just what this says. So the slide is just a repeat of what we've already discussed, but that's how signals work. They're indirect. And a nice thing about it is a quick way of hitting multiple threads with a notification. Whereas message passing would require you to send a message here, a message here, a message here, a message here to hit multiple threads with a message. Make sense? So signals are kind of the more Cowbell version of this. Speaking of which, how many of you are going to watch Peter Pan on Thursday? Is that tomorrow? Do you know what I'm talking about? There's like a live Peter Pan thing on TV with Christopher Walken playing Captain Hook.
Exactly. He's the only reason to watch.
I love Christopher Walken. There's a comedian who does a really good impression of Christopher Walken, and he tells this. He plays it off as it's a true story, and I guess he was at some party, a celebrity party, and he comes outside. He sees Christopher Walken just out in the driveway, just looking lost, and he's like, "Hey, Chris, can I, you waiting for somebody or something like that?" It's like, stranded. I guess his buddy had left him. He says, "Well, do you need a lift?" Like, please. So they walk out to his car, And the guy had one of those remote starts for his car. He turns his car on, the lights come on. Because Christopher Walken like jumps back, goes, "Wow, your car, it's alive!" And then the guy said he got in the car, and Christopher Walken like stared down the headlights of this car for like 5 minutes, and then finally just goes, "Chase me." And he tells his story as if it's like this is not made up for comedy, like this happened. Yeah, I love that guy. Apparently, it's very difficult to work with him because you think he's being funny on stage, but he's really just crazy. See, I aspire to that. See, I feel that I still have like a little bit of sanity left. Him, it's gone. How did Christopher Walken come up from signal handling? Ah, Peter Pan. How did Peter Pan come up from?
Well, because you said that you were saying something about more cowbell.
More cowbell, Christopher Walken, if you recognize that from the Saturday Night Live skit. Remember that? You don't know? Yeah, Christopher Walken was supposed to be like a big music producer. And Will Ferrell was in the skit when he was still on Saturday Night Live, and there's like a band practicing, and Will Ferrell's playing the cowbell in the back, and like from an audience perspective, you think the cowbell is like incredibly distracting, like just ruining the song. And Walken comes in, and he's like, "Look, we're really gonna need more cowbell," and he's like, way too much cowbell already. And
Don't Fear the Reaper.
oh my gosh,
Don't
fine.
Fear the Reaper. That was the song that was putting cowbell in.
Is this the? You're not going to show it? I hate those. All right. Which one?
2, 3, 4.
Nope. Let's just get rid of the. This is the one I already clicked on, right? No, maybe not.
That was going to be a great track. Guys, what's the deal? Are you sure that was sounding okay? I'll be honest, fellas, it was sounding great, but I could have used a little more cowbell. Cowbell.
This isn't going to happen. I know it's not going to happen. Let's see if we can get to, this is like several.
From Chevrolet,
Maybe we
the
can
first and
get to the
only car
exact
company
spot.
to bring built-in 4G LTE Wi-Fi to cars, trucks, and crossovers.
Live from New York, they're the skits that...
So does.
I love those, the Celebrity Jeopardies.
Yeah. The Sean Connery.
Sean Connery.
is the best.
Once again, Sean Connery, please refrain from using racial slurs.
Yeah, that's right.
Oh, yeah. Oh, there you go.
Is this the sweaty balls one?
Pants on, just like the rest of you, one leg at a time. Guys, I put my pants on, just like the rest of you, one leg at a time.
Number 1.
Except once my pants are on, I make gold records.
More cowbell. If a skit spawns a catchphrase beloved by an entire generation, it's a hit.
I could have used a little more cowbell. Really explore the studio space this time.
You got it, Bruce.
I mean, really.
Will Ferrell is one of the biggest stars ever to grace the SNL stage. And we've established that Chris Walken is a killer host.
You're gonna want that cowbell on the track.
Tack on porno stashes, Ferrell's tiny shirt, Fallon's incessant giggling, Walken's deadpan dialogue, and, of course, the cowbell itself. And you get fireworks. Or at least a temperature of some kind.
I got a fever. And the only prescription is more cowbell.
Do you agree with our list?
You at least got a taste. It was number 1 on the list. So, worth it. And they have a female playing Peter Pan, which seems weird. But,
They've done it before.
no, I know, but why is that? Because the person's name is Peter.
I'm sure it's like to get the whole, like, he's supposed to be young, so they get the husband's voice.
Why don't they just cast a young male? Like, actually make the person, like age-appropriate person.
This is theater, nothing makes sense.
I guess that does make sense, seeing as though they've cast Christopher Walken in. So, I'm looking forward to Christopher Walken being a crazy Captain Hook. All right. Thread pools. Create a number of threads in a pool while they await work. So, kind of the idea of this would be, I think last time we talked a little bit about authentication, where if you were logging into Amazon, every single time somebody dialed the phone, went to Amazon's IP address, somebody would pick up, spawn off a thread, hand off the authentication step to that thread, and then go back for listening to the phone call. So if you think about the just like we talked about context switching on CPUs being expensive, spawning off a thread is also expensive. And if you're going to have, let's just say 1,000 hits per second, just throwing a number out there for how many people might be hitting Amazon every second. If you're spawning off a brand new thread of execution for each of those people 1,000 times per second, you're going to lose performance. And you might have some timeouts and things like that. So a better approach is to create a thread pool. Well, when the server first comes up, maybe Amazon's login server is probably a pretty beefy array of computers, not just one computer. So what they're going to do is, as part of the startup sequence, they'll probably spawn off 1,000 threads, 10,000 threads, whatever. So you just have a whole bunch of worker bees just standing there ready for you to hand them work. Okay? So now when somebody connects, rather than having to create a new thread and telling it to start, what you do is you just pick the next thread, hand them the guy, and say go. You don't have to spawn it off and do all the startup stuff that involves creating a new thread, dividing up CPU time amongst them, that kind of stuff. Make sense? So we push all that time, that startup time, to when the server first booted, when it first came online. So that takes a little bit longer for the server to come up. But once that's done and all those threads are up and running, now we can just tell them to get to work whenever we want. So slightly faster, that's going to scale depending on the problem you're solving. So rather to request an existing thread rather than create a new thread, I don't even think I agree with the whole slightly faster thing. It's probably several orders of magnitude faster, really. So in terms of human perceived time, spawning off one thread versus accessing an already created thread is probably going to be imperceivable for a single thread. But if you looked at actual CPU cycles, I would guess that spawning off a brand new thread is probably 5 times slower. That's like based on just a complete guess, but something along those lines. Several orders of magnitude slower. Then also allows the number of threads in the application to be bound to the size of the pool. This actually is kind of an interesting spin that we can even connect to the thing we were talking about with the game last night. The game that I play and Jake also plays had a boss guy that spawns off extra ads. These guys that autonomously go and attack people. So each of those ads are going to be stored in their own thread. Okay, so they have their own mind, if you will. Well, it seems like when they spawned off these ads, they had an infinite loop somewhere, and the ads just kept spawning over and over and over again, and they ended up running out of space. My guess is, and just trying to connect it to this example, who knows, this might not have been the problem, but chances are they spawned off each ad as their own thread in real time, rather than having a pool of ads. Here's the maximum number of ads we can ever have, and pulling from that single pool. Okay, so threads do deplete the performance of a machine. So the more threads you spawn, the more sluggish the machine is going to get, or at least more sluggish the process is going to get, because that process is now sharing its CPU time across 50 threads, 60 threads, whatever it is. So from a performance perspective, when somebody's writing an application that's a multi-threaded application, there does need to be some consideration with how many threads do we want to allow to run at any given time. What's the maximum worst case scenario? Yeah.
So you're saying, like the example of Amazon, maybe they have the thread pool, but then does that mean they can only have a certain amount of people hitting their server?
Not a certain number of people hitting their server, but a certain number of people that could be authenticated simultaneously. Because each of those thread workers is going to go and do the authentication job, where they're going to read in the username, read in the password, authenticate them, and say, here's your unique code that says you're authenticated. Talk to you later. Go get back in the pool of threads ready to authenticate again. So that thread pool size would really dictate how many people can be authenticated simultaneously, not how many could be on the system at once. Because once you're authenticated and you kind of have your boarding pass, if you will, that thread isn't working with you anymore. Now you're making requests on the site, passing it along your credentials saying, I'm good. You've trusted me already. And now it knows who you are. So that's not a thread working with you. That's just a web server request, which would have its own threads. But those are handling individual little requests. Give me XYZ page.html, something like that. All right, so limiting the number of threads that a system might have at any one time is a performance consideration. Thread-specific data, we've seen this with Java, where we actually create objects themselves that are extensions of threads, and those objects get to have their own, their own fields and stuff like that. If we want one thread to keep track of usernames and passwords, and another thread to keep track of, a list of data points or something, they could certainly do that. Because a thread is not a generic entity. Threads are custom built for the type of work that they're supposed to do. Not dissimilar to real life. If you need a bunch of people who know how to detassel a field, you're going to hire people who you're going to hire people who know how to detassel a field. You're not going to hire probably a bunch of brain surgeons. You're going to hire somebody appropriate for the job. So in computer science, you're going to build an object that is built to do the job that you need it to do. Stupid. Okay, this is kind of the, a picture that shows I don't know what this shows, but something. But this is kind of the perk of threads. Threads are considered to be lightweight processes, whereas the fork command produces an entire process that has everything associated with it, the CPU time, the list of registers, all that stuff. So, they are big box items, if you will, where threads are, in little packages. So that's the plus side of threads, is they take up less system resources. The downside of threads is they also share system resources with the parent. So that's the trade-off. Okay, this is just examples of threads. Dum. Chapter 4 under the done. Chapter 5. Oh, good. Should be able to chug through this pretty quick. So we already know what CPU scheduling is. This is the job of making sure the CPU stays busy as close to 100% of the time as possible while still making the end users happy that everything seems to be happening all at the same time. Let's see. This guy's going to specifically talk about a couple of scheduling algorithms, so that's where we'll take it one step deeper than we've talked about at this point. So basic concepts, maximum CPU utilization, CPU I/O bursts. So process execution consists of cycle of CPU execution and I/O waits. So that kind of goes hand in hand with this idea of maximum CPU utilization. Things that are on the CPU should be things that are not waiting on I/O. And then playing that game of how often to context switch. Okay, dumb. So this is the queue stuff we talked about. CPU scheduling, waiting state, ready state, blah, blah, blah. Dumb. We have this aspect, this might be a thread of the CPU scheduler called the dispatcher. So this guy's in charge of sending the people into the CPU and getting the people out of the CPU. So switching context, switching to user mode, jumping to the proper location of the user program to restart the program. That's part of the context switch. So we have the program counter that tells us which line of code comes next. So the dispatch latency that discusses here, time it takes the dispatcher to stop one process and start another, that's context switch time. To context switch in and context switch out and context switch in. That's going to build into the latency. So kind of criteria that the scheduler is going to use for its scheduling decisions, and there isn't a right answer here. And we'll talk about some of the algorithms here shortly. But one criteria, keep the CPU as busy as possible. That's kind of your global goal that we never meet. We've talked about that the CPU sits idle a high 90% amount of the time. CPU is idle most of the time. So throughput, getting as many processes done in a single period of time. And that becomes kind of a guessing game as well, because some processes just run in perpetuity on your machine. They don't start and finish some number of cycles later. If you have Microsoft Word open and you leave it open for a month, I mean, how many of you have applications on your computer that have been open for just a long time? If I just do here, I have Keynotes open always on my my laptop, Safari, QuickTime, my email's always open, iMessage, Preview, I have a PDF usually up, and I keep Eclipse up, and sometimes the terminal's there. But these are the things, these are user applications that I purposely keep running, not to mention the stuff that's running in the background all the time. So things running to completion on a user-centric operating system isn't necessarily a real criteria to consider, because we're really guessing at what the user is going to do. Now, in batch processing-based operating systems, where they basically take in work, complete the work, ship it out, criteria for getting things done in the most efficient amount of time makes a lot more sense. Put yourself in the shoes of, let's say you have 30 chores to do around the house. What would your mentality be for scheduling those chores to get them done in the most efficient amount of time. Make sense? So it's it would be that kind of mentality for a batch processing type of scenario. Turnaround time, we've discussed about this a little bit. We didn't call it turnaround time, but the amount of time that we give to a specific process on the CPU before we context switch it out. What's too little? What's too much? Give something too long on the CPU, the end user is going to feel like they're not getting CPU time for programs that they might be interested in. Too little, we spend too much of our time context switching. What's the sweet spot there in the middle? So that's another criteria. Waiting time, amount of time a process has been waiting in the ready queue. So something we're going to talk about here, somewhere down here when we get into the algorithms, is the priority of processes. So certain processes are going to have higher priority than others. So if you think about it, when you're using your operating system, whatever program you currently have open and are using is probably going to be a fairly high priority process, right? The 4 things you have in the background, for instance, right now, I have Eclipse in the background, and we haven't even looked at Eclipse today. From an end user perspective, I want Eclipse to have a pretty low priority. I have it open specifically so I can quickly switch to it if I want to, right? But I don't want to really get much CPU time right now, more than the bare minimum to just keep things kind of chugging with it. Because I care most about Keynote being responsive for me. But in a situation where something's been sitting in the ready queue for a long time, at that point we might still give it some CPU time to kind of keep it going. And where this is most evident, I may have brought this example up one other time that dealt with how multitasking was handled on older operating systems. The older Macintosh operating system, OS 9 and earlier, used a model called preemptive multitasking. Did I just talk about that at all? Remember what I'm talking about ish? So, and the best example of that would be you start, and this was really noticeable because it was in the early days of the internet when people started downloading stuff. Now we don't think of downloading stuff off the internet as being something special, right? But the ability to download stuff was a big deal back then. So if you got something downloading off of the internet, you'd open up your Mosaic web browser, or maybe Netscape, the one with the purple N that just pulsed. Any of you seen that one? Before your time? How many of you have ever used Netscape? Netscape existed for a while, then it turned into the Firefox project. So Firefox today is what's left over from Netscape. So after the original pulsing purple N from Netscape, then you had like the N with the stars and stuff lying around it, that kind of crap. But in any case, you'd open up Netscape, you get something downloaded, then you'd put it in the background. And there wasn't a such thing as minimizing it. You would just bring another window to the forefront. So you'd be working on Microsoft Word, writing your paper or something, go back to that download an hour and a half later to recognize that not much has happened. It was getting the bare minimum of CPU time just to keep that process alive. So it wasn't getting access on a very regular basis to any sort of I/O, which was a problem because when you're downloading something on the back end, you're writing that to the hard drive, right? So you're grabbing a bunch of stuff off the internet, storing it as some sort of buffer, and then when you're off the CPU, putting your buffer onto disk, onto the hard drive. Okay, so that's when you go into the I/O queue. So that's kind of how it would work. Well, that wasn't happening while it was in the background, or was not happening very often. You would make progress, but if you were downloading something at, I don't know, a really fast speed back then at like 1.2 kilobytes a second, which was, once upon a time, that was ridiculous. Like, you're getting a K per second? Wow. Before that, it was bytes per second. That's when modems were measured in baud, B-A-U-D. How many bits per second does it allowed them to put a bigger number. This is 57,600 baud modem. That's how many bits per second max I can transmit. And it's all based on how much line noise there is on the telephone call. What's it talking about? Okay. So that's turnaround time. We talked about waiting time. Response time. Amount of time it takes from when a request was submitted until the first response is produced. So this might be for a time-sharing environment, specifically situations where you have multiple users using one operating system, like in a Unix operating system type situation. When you first launch a program, you care the most about the performance of that, or you notice it the most the first time you launch it, right? When you double click on Microsoft Word, if it took a minute to launch, you're going to be ticked. From that point forward, if you're using Microsoft Word and you click on the File menu, so I come up here and I click File, if it takes 1 microsecond or 14 microseconds, we care less about that. We don't feel those small little delays. Make sense? But that initial delay when the program is having to do the most, you know, like we used the example a few minutes ago of maybe Amazon server booting up their server software is spawning off 1,000 worker threads. That might take some time. But on that particular operating system, the priority is we want to get that server up and running. And if everything else has to wait, so be it. Okay? So again, this kind of paints this picture of not all operating systems are created equally, and coming up with a scheduling algorithm that meets the needs of the end user is problematic. And it's kind of what we don't necessarily see it, or it's not advertised to us greatly, but we are at least aware in here that usually there is a Microsoft Windows Professional, whatever, the user version of it, and then there's usually Windows Server, right? Okay. While they have the same core NT kernel for the operating system, the decisions that it's using for scheduling may be very different. Okay, because for the server, typically it's not going to be used by a human being directly very often. Only when the network administrator or the server administrator is sitting in front of it, actually installing a program or something like that. They're not probably going to be writing term papers and playing video games on a running server. You know, some of us at home, we might run servers and we kind of have a multi-purpose computer, right? But if you've installed something in a server environment that's supposed to be Amazon's web server, probably not playing World of Warcraft in that machine as well. And it has a different priority set. So the idea is it's going to pay less attention to making the end user happy, end user being the system administrator who's probably using fairly generic tools. Any of you done any server administration stuff? How many of you are IT majors in here? Assuming several of you, right? Rest of you computer science traditional? Proud of you. And I mean that in the most disrespectful way to the IT people. No. Yeah, what I tell people when they come in and can consider Concordia, since we have two programs, I say that IT and computer science are opposite sides of the same coin. Computer science is about 70% creation, 30% utilization of what's been created. IT is about 70% utilization of what's been created, 30% creation. So that's why programming is still important for the IT side, but it's 30% of what you'll have to do. But my point was, if for any of you who have done some server administration, and you'll end up doing it when you go through the IT experience, typically when you launch one of these applications for managing user accounts or managing processes that are running on the system and stuff like that, they're very bare bones. They're not real flashy applications. They're functional. Part of that is, and they're probably actually more so that way now than they really ever have been. Part of that is to take a minimal system resources, because keeping in mind the operating system is probably not going to give as much priority to the person who's actually using the system, but also because it's very common for people to remote in to servers to administer them. I think that's right. to administer them. So the idea is, how many of you have ever used one of these remote desktop type things? Log Me In or Go to My PC, one of those guys. If you are having to restart a torrent download or something like that, not a big deal, right? Those are fairly graphic intensive type things. What if you were going to play a video game over Log Me In? Probably not going to cut it, right? Really, Log Me In is loading your desktop as just a bunch of individual images. So if you're sitting in front of your computer and you can get 50 frames a second in your video game, through Log Me In you're going to get about 4 frames a second.
I did that on my iPod Touch one time.
Oh, play the game? But did you,
Yeah.
right, but did you use, you didn't use Log Me In, did you?
Yep.
Really? Did you actually play? Like,
Yeah, I was able to. I mean, I didn't like. I mean, I could move around and stuff. Like, I did what I needed to do, and then I.
Okay.
Stopped. I mean, it wasn't a good experience, but.
yeah. I've done that before for botting.
Yeah.
To start or stop a bot or move the guy to another location, but you could, I mean, I wouldn't view it as being playable.
Yeah.
I suppose if you were running a server and you were on the same network, so if you're on the local area network, Log Me In might do something where if it notices you're coming from the same network, it just allows you to do a direct connection over the local LAN rather than hitting their server and then coming back down. That's possible. I know there are a couple of remote desktop solutions out there that are geared towards gaming, where they try to stream the graphics more quickly, so it's very much focused for that specific application. But generally speaking, the punchline here is that server admins are likely going to be remoting into a machine, so at 4 in the morning when the web server goes down, they're not having to get in their car and drive over the campus here or something like that. They can remote in, restart the web server, and at least do the initial troubleshooting from a distance. Make sense? So these are all things that go into the scheduling part of how an operating system works, and they're not all created equal. And this is just a list of what, these are the same slides. This is just a waste. This one has text after it. This one just lists them. Just stupid. Okay, so just to kind of give you, we'll just start the discussion of specific algorithms. The most human algorithm we'd look at is first come, first serve. If you get to McDonald's and you get in line first, you're going to get to place your order first, right? That's human fairness. Doesn't always make sense, though, in computers. But human fairness, first come, first serve, is going to be the one that we come up with first. Okay? So I'll see everybody on Friday. We will talk about the final exam. First thing on Fridays, we make sure we have enough time on that. Then we'll keep talking through this and try to get as far as we can. Just if you want to start preparing, final exam will be cumulative. And I'm going to try to make it as ridiculously impossible as possible. It's a hobby. All right, I'll see everybody Friday.